So welcome to this joint CASE, Center for AI in Society, and ORI program seminar. Thank you so much for joining us and braving the rain. I know for LA it's very challenging. So before we get started with introductions to our speaker, I'd like to just make a quick announcement from the CASE side of things. So the Center for AI in Society is kicking off a new student-led group exploring how tech can tackle big social issues. If you're curious about how AI and technology can support mental health and well-being, join us for the first Tech and Mental Health Group meeting, which is happening virtually this Friday at 12 p.m. You can check your emails for an invite that just went out. You'll hear short talks from the CASE student leaders on their projects, and then we'll have a quick networking session to explore collaboration opportunities and come up with ideas. Whether you're into mental health, AI, or just curious, this is the perfect space to connect with other folks. Please check your phones for the invite now. So this is a message from our CASE leaders, in particular from Jaspreet, that many of you may know. And now on to the introductions to our speaker today, Professor Pascal Van Hentenryck. So Pascal, he's a great fit for both our seminars, for both CASE and ORI, because his research really bridges AI and OR to address important engineering social problems. So Pascal is a professor at Georgia Tech, where he also directs the NSF AI Institute for Advances in Optimization. He's fantastic speakers, and I'm sure he'll all get you excited about getting involved in this kind of work. So please join me in welcoming Pascal.
Thank you, thank you, Phoebe. Good afternoon, everyone, and I'm super happy to be here with you. I first want to thank Phoebe and Bistra for inviting me to be here on this campus with wonderful weather. I also want to thank the team that is behind some of the results that you have seen. It's the work of a lot of people, not only my work, and you'll see some of the references as I go over the talk. So this is essentially the mission statement of the NSF AI Institute for Advances in Optimization. So what we are trying to do is design, fuse AI and optimization in such a way we deliver outcomes that could not be achieved by the two technologies independently. So it's not incremental research. We want to actually do a big step forward and show that there are applications that can now be solved and that we could not solve a few years ago. And I hope by the end of the talks that I will convince you that we can do some of these things. So this is essentially the outline. I'm going to talk about optimization proxies first, after the motivation, learning to optimize, learning decision rules, mostly for sequential decision making, and then talk about contextual stochastic optimization and the use of different new techniques in there. So that's the program. I'm going to start with some motivation. So I'm an optimizer by training. So essentially what I love about optimization is that you build a model, you get some input, you put it in the solvers, you click a button, and then you get an output, which is an optimal solution. When it works, it's amazing. And it works, most of the times. But there are circumstances where it's too slow, and that's what the talk here is going to focus on. Either because you have real-time constraints, you have to deliver a response very, very quickly, or you have planners in the loop who typically don't want to work an hour before getting an answer because they have to run through many, many, many scenarios, which is like also the last application. When you do some of the platforms that I'm going to show you later on, you run a massive number of simulations, and you have to run them fast. Otherwise, it's not going to be giving the right information for the decision makers. Now, what is nice is that we live in the real world. And in the real world, those applications typically are on big infrastructures that don't change very fast. If you have a power grid, you don't build a transmission line every day. When you work in port logistics, you don't bring a new crane every day. And when you work on manufacturing problems, they don't open a new assembly line every day. So these are relatively stable situations. And what I want to show you is that most of the time you're going to solve the same problem over and over and over again. And most of the solvers don't learn from that. They essentially throw the past completely and they resolve from scratch. But we typically have massive amount of information about the past or potentially from the future if you have good forecasting method, and we are not leveraging that. So what are we solving? If I had to formalize what I just told you, is that we are solving parametric optimization problem. It's the same problem, the same structure all the time. The only thing that is changing is the data. And so in this particular case, X is the instant data, and the objective functions and the constraints depends on it. But the rest, the structure of the constraints is exactly the same. And so we want to solve these parametric optimization problems for applications where we have a lot of historical data, but we also have real-time requirements. So you can view an optimization solver now as a function from this input to output. And this function, this is very nice, because as soon as you view the world as function, you're going to see, hey, can I apply machine learning? Because machine learning is a universal function approximator. You say, wow, this is fantastic. I don't have to optimize anymore. I can learn the optimization, use my machine learning model, and now I can do this very, very fast. So in other words, if I'm trying to formalize that, you have a set of input and output. The input to your optimization problems, the output. You build your architecture for machine learning, which is parameterized with some parameters. And then you minimize a loss function for finding the best value of these parameters. And typically, the loss function is going to be the difference between what you're predicting and the ground truth that you have obtained using the optimization solver. So why is it this and you can solve this, and you can tune this using stochastic gradient methods. And so when you do this, what essentially you're doing is that you are putting a lot of the computational burden offline, and in real time you can apply this model, and it takes milliseconds to solve it. All right? So this is what I'm proposing to do. So does it work? This is a binary question, 0 or 1, yes or no. Does it work? I'm asking this question all the time. Very few people are willing to answer. Does it work? Well, I give you a hint. If the answer was yes, what would happen to this talk? It would be finished. Okay, so it's not yes. Okay, so the problem is that in practice, we have a lot of constraints, and some of these constraints are hard. You can't violate them, and they can be physical constraints or engineering constraints or business constraints, but the machine learning model, being a regression by definition, is not going to satisfy them. And so what we need to do, and this is the purpose of the first part of the talk, we need to have a good approximation. We need to kind of having an AI system that's going to use machine learning, but use other things, such that we have these 3 things that I really want. The first one is reliability. I'm always going to produce a solution that satisfies those constraints. The second thing that I want is a performance guarantee. I want to know how good I am. And then I want to scale that. And some of the problems that you're going to show, that I'm going to talk about, have millions of outputs or millions of inputs. It's not very large-scale problems. So I want to convince you that I will be able to do that. And that's the first part of the talk. These are the concept of optimization proxies. So this is, at a very high level, the infrastructure that we are building. So you have your machine learning model, which gives this nice approximation. It's almost right. But then we have a repair layer, which is going to basically take that approximation and transform it into a feasible solution. Okay, so this architecture, if we can make it work, is always going to return feasible solution. So in a sense, so this is a very simple example. I have my neural network for 2 inputs. I have a linear program there. You can see the feasible region. And what you can see here are 3 things. You can see the machine learning model. You can see the optimal solution in red. And then you see the proxies. And one of the nice things that you see here is that the proxies is going to be almost always on top of the optimal solution. But the machine learning model is very often, almost always, outside the feasible region. You saw it there. So what we have to do is that this repair layer has to take this, a machine learning model and project it into the feasible region. So that's what it's going to do. So in a sense, you can formalize that by having a projection method. You're basically taking something which satisfies all the constraints, but stay close to the prediction that you have done, but make sure that all the constraints are satisfied. So at a high level, that's what we're going to do. Now, we want to still continue to train this using stochastic gradient descent, which basically means that we will have to backpropagate through the repair layer. And that's one of the challenges that we will have. Okay? Some of you work with Bistra, so you have seen this before. There was this amazing theorem by this French mathematician. What I love about when you look at all these results from mathematicians from the 18th or 17th century, they prove theorems that may seem completely arbitrary, but now they become useful like 3 centuries afterwards. And so the key idea here is to think about the fact that you could have your pipeline, your machine learning pipeline, with some of these repair layers. And if these repair layers are solving a set of equations, there is a beautiful beautiful result by Cauchy, which says that you can actually, if you think of the solution method of the equation, kind of the function that we, given an input, would give you a solution to the set of equation, that function is almost never in closed form, but its partial derivatives are. Now, this is called the implicit function theorems. And so this is the explicit form of the gradient that you can use in backpropagation, right? So in the forward propagation, you solve the system of equation. And in the backwards, you use this particular explicit form for computing the gradients. So that's what I just told you. No, you may say, hey, but this is an optimization that you wanted to solve. This was a projection. How do you do that? Well, typically what is happening is that when you solve an optimization problem, you have optimality conditions. These are a system of equation. It's like you're solving a system of equations. So in the backward phase, you can just use the implicit function theorems to do that. Now, there are some issues with this. It can be very slow at training time. So are you willing in your application to do this? Or in sometimes, if your problem is too complicated, the optimization problems may not have meaningful gradients. So I will show you how we can actually address some of these concerns in some of the applications, because sometimes you can do better by exploiting the structure of the problem. All right? So the second thing that I want to tell you, assume that we can do this. No, we assume that we can do this. I'm going to talk about another problem that we have to face. We face the curse of, generating the data. Because one of the things that I told you is that we need these pairs of input, the input to your optimization problems is also the output. So we have to solve a massive number of optimization problems offline. And that may take a very, very long time. So can we do better? And so this is where we have, there is an idea that I truly love. And when we can do this, this is like magical. So this is a robot learning it, on its own. What does that mean? That I'm going to do self-supervised learning. And so we are in a very unique situation here because we have these parametric optimization problems. So I know what my problem is. So if I have an input, I know, what I'm trying to optimize. I have this function f that I'm optimizing. So instead of having a loss function, since my AI system, my optimization proxies is going to give me feasible solution, instead of having, trying to, do a loss function which depends on my prediction and the optimal solution, I can directly look at the optimization function. So this is the idea. So I'm going to basically train this model using the real optimization function and then do a backpropagation through it. I don't need to have labeled data. I'm using directly this. Okay? So let me show you more in symbols here. The only thing that I need are the inputs, and it can be a complete distribution, infinite distribution if I want. I have a parametric optimization model, and this is how I train. And this is a very interesting optimization problem because it has my proxy there that you see. It has also the real objective function, but it's not the same optimization as what or the instances that I was trying to solve, because what I'm optimizing here are the parameters of the machine learning model. But it's kind of funny because it resembles, in a sense, the real optimization problem. Okay? So that's the second thing that I'll tell you. So far I told you we can actually build these optimization proxies that are guaranteed to find feasible solution. And the other things that we can do is, use self-supervised learning. You don't need labeled data for actually solving them, at least in some of the applications that I'm going to show you. Now, as an optimizer, when I tell my students what optimization is, I tell them this is two things. Optimization has to be two things. One is finding good near optimal solution. And the second thing that I want is that I want some estimation of the quality of those results, because I don't want the next consultant to say that they can do better than I am, right? And so I want to see, no, I have this proxy. I know that it's going to give me a feasible solution. Can I give guarantees? Can I tell, the person with the problem, my stakeholders, can I tell them that, the quality of my proxy? And so I'm going to show you something which is truly beautiful. I mean, duality is one of the most beautiful concepts in optimization. And we are going to explore the fact that we are in the real world. What is happening in the real world is that, in general, every decision that you are going to do is bounded. You have bounds on it. When you generate electricity, your generators is bounded. When you are trying to schedule, let's say, a logistics system, you have a finite number of trucks. And so you have bounds on these variables. And these bounds are super useful because they give you variables and dual variables in the dual of the problem which are free. And this is amazingly useful. Because now if you want to build a dual proxy, okay, for finding a bound on my objective function, I can predict the y in the dual problems, and I have the flexibility with the lambda and the gamma, the dual variables associated with the bound, to actually restore feasibility. So I have a super simple way of restoring feasibility in the dual. Okay, and this is really, really nice. So in a sense, my proxy now is a proxy where I only approximate, give an estimate of a partial of some of the dual variables, so it's a partial dual solution. But then I have a completion layer that will actually find a feasible solution using these 3 dual variables that I have. Okay, so this is cute, right? Come on, you have to give me some energy here. Yeah. All right, so you can generalize that to to any convex programs essentially by using another step there, which is a conic projections. I won't go into the detail. This is a paper that we published at NeurIPS last year, but roughly speaking, this is the same thing for second order cone or semi-definite programming. You restore feasibility in the cone, and then you use the dual completion for finding a feasible solution. So this is cool, right? So I told you a couple of things so far. I told you, number one, that we can find these optimization proxies to find good quality primal solution. I told you that I can give guarantees. When I run in milliseconds now, I will give you a primal solution and I will give you a dual solution, and therefore I know the bound. Okay? Now the problem is that sometimes when you train these models, when you train, for instance, a primal, you will be very, very good in expectation, within, let's say, 0.5% of optimal, but you will have these outliers, and this is also annoying. Okay? Now what I'm going to show you is the last piece of the puzzle, where we're going to take the primal model, the dual model, and we're going to train them together. Okay? And then my loss function is not going to be the optimal, the objective of the primal or the objective of the dual. It's going to be the duality gap. And so I'm going to train my model in trying to minimize this duality gap. So instead of having the real objective function here, I'm basically using the primal objective function, the dual objective function, computing the duality gap, and that's what I'm minimizing up to a certain tolerance. So now this is really nice, because you're going to do something which is really giving you removing these outliers, because what you're going to do is train the primal model, get a primal solution, use the primal model that you have trained jointly with the dual model, use both of them to get a primal and a dual solution, compute the optimality gap, and if this optimality gap is too large, you can always call the optimization solver. But you will call it only when you actually identify these outliers. So this is a super cool idea, because from now on, I have complete guarantees, and I will not have, not only in expectation and not only in real time, but I know that at the runtime, I will be able always to find the solution of the quality that I want. Okay, this is a paper that we are finishing today. So I'm going to start giving you some examples now. So you have seen what we can do. We can always do primal solution, give us certificates of quality, and if the quality is not there, we can use the optimization solver. So I'm going to tell you a little bit an application in power system. I will move to the supply chain later on. But this is what I want to show you is how you manage a transmission system like MISO. MISO is the Mid-Continent System Operator, which runs the grids from Canada to New Orleans. And we work with them on a project where the goal was to see if we can push renewable energy. They have a lot of wind in the north of the system, and how we could actually manage the risk inside the system. So this is how you run a power system in the United States. So you have to make 2 important decisions. Commitment, which generators are going to be committed to produce electricity for the next 24 hours. And then you will have what is called economic dispatch, where you decide every 5 minutes how much every generator is generating. Okay? And so this is the pipeline of something like that. I'm going to go over it. The day before, 10:30, all the bits are coming, and you decide which generators are going to be committed for the next day. This is only based on the bit. About 80% of these bits are actually virtual bits, people playing the market. Then, these bits are not necessarily truthful. So a couple of hours after, about 6 hours after, what you do is you use the forecast for the load, the demand, for the renewable energy, wind and solar, and you do what is called a reliability unit commitment. And one of the things that can happen there is that you're gonna start new generators, because you may think that you may not have enough resources. You can do that every 5 minutes. That's a look-ahead commitment. It's also a reliability commitment. But then the most important thing is the real-time market. Every 5 minutes, you try to match the consumptions and the production. Okay? So this is at a very high level. It's simplification of how this works. This is the economic dispatch, which is essentially in abstract form, but this is what is run by MISO and other ISOs. So the first equation that you see there is non-negotiable. You have to make sure that you produce as much as you consume and not more, because otherwise, the system is not going to work. Then you have the reserve constraints, making sure that if something happens, you have enough reserve to catch up. And then you have the engineering constraint, non-negotiable as well. And the line constraint, these are the thermal limits on the lines, are typically soft constraints, but the penalty in the objective function is so high that they are satisfied 99.99999% of the time. All right? So I can't show you US data. This is French data. What you see on the left is the energy of the system, the economic dispatch every 5 minutes. You see that it changes a lot. The big circles are nuclear generator. Yellow is solar, and then you see wind as well. What you see on the right is the reserve. And one of the things that was striking to me when I first look at this is how much things are changing. It's the same problem, but different instances are going to give you very, very different results. And so this is what we are trying to solve. Now, this is working, currently. But one of the things which is happening is that we are pushing more and more renewable on the grid. We are having, using batteries. The data centers are consuming more, and the load is much more difficult to predict because now everything is essentially electrified. Cars, also solar panels on the roof. Households have also batteries, which make everything much more difficult to predict. And so what we want to optimize, what we want to avoid is this. This is a real picture. This is what happened in Spain about a couple of months ago. They had oscillation in frequency because of the renewable, and then they disconnected the HVDC line with France, and then all kinds of things happened. And you had a blackout, which I think lasted about 24 hours. This means no electricity, no refrigerations. It also means no cell phone, and so people were completely lost. They couldn't do anything. So what we need to actually address those things is with better tools. And one of the things that we are building is just this real-time risk assessment platform. And so the way this works is that the day before or every 15 minutes during the day, we want to simulate what can happen in the system for the next 24 hours. And so to do that, what you're going to do is generate a massive number of scenarios that you see there. And then for every one of the scenarios, you have to solve all these economic dispatch, about 200, 300 of them. And the whole thing here for one simulation is, for 24 hours is taking about 15 minutes. Now, you want something that is a real-time tool such that the operators can adjust what they want. So 15 minutes is not going to be sufficient. So what are we going to do? We need two things. The first thing we need is crystal ball, and this is like predicting what the wind can be, what the load can be, what the solar, how much solar energy you get. What you see there is essentially a prediction of the wind for the MISO system. This is based on a public data set, so no confidential information here. But what you see is that we have to predict about 10 to the 4, more than 1,000 different time series together. So this is based on things which are called temporal fusion transformers. This is like the transformer architecture, but also more layers, still LSTM layers and variable selection. This is the, what you see inside is the self-attention mechanism there. And so that's generate quantile for quantiles for every one of the wind farms or the solar farm have every time series that you want. But when you generate a scenario, you have to make sure that you capture the correlation, and that's what you can do with the Gaussian copula. So roughly speaking, you use also as much information as possible about the future, like the forecast for the weather and so on. And what you get at the end is something which is highly accurate in a sense, as far as these kinds of technologies are, because the wind is very difficult to predict. But you can see that the load is typically within 1%. The wind is about 8%, and then solar is about 3% accuracy, which is kind of really enough for generating a very nice set of scenarios. So that's the first thing. Now we have to keep the lights on, which means that I have to build a very good proxy for trying to speed up on my optimization. So what do? I have essentially the machine learning model, which is going to predict my approximation for the power of every one of the generators. But now I have to restore feasibility. And so there are two things that I need to restore: the power balance, which is non-negotiable, and then the reserve. And so one of the things that we did there is not really using Cauchy's theorem, but we can actually use ID from control to do better. And the first thing that you see there is that what we do here is that if we don't have enough power, we need to increase every one of the generator proportionally or proportionally with some weights, or we decrease the power if you have too much. And the beautiful thing is that when you think about this, you can actually generate this formula that you see there, and this formula are super beautiful. Why are they super cool? Because they are differentiable almost everywhere. And so we can generate this formula very quickly. Obviously, they will change, for every forward pass of your machine learning model of, training your proxy. But they are differentiable everywhere, and therefore you can do backpropagation super fast. And so in a sense, you compute these things in the forward pass very quickly, and you can backpropagate very quickly. The reserve are a little bit more complicated. You have to split the generators in two phases, in two sets. The first one are the cheaper generator. And what you do there is you decrease the power, but you increase the reserve. But if you decrease the power for these generators, you have to increase the power of other ones. And so this is what you do there. For the generators which are more expensive, you can increase the, because they are expensive, they are not used at their capacity, you can increase the energy that they produce and keep the reserve that they have. Once again, this is going to be a complex a reasonably complex algorithm for generating, again, some formula that are differentiable almost everywhere, and they have subgradients everywhere. And therefore, you have this very nice proxy now, which is essentially a machine learning model, and then these layers, which is very, very, very nice to compute and to train, and very efficient to do that. And so what you get is this kind of results. Okay, so you can train your system, your optimization proxy, for the economic dispatch, and it takes 10 milliseconds to run it. You can train it in about 30 minutes, which basically means that even during the day, there is a change, like it's raining in California and you didn't expect that, you can actually retrain it very fast. And so training takes about 30 minutes. This is the kind of optimality gap that you get, except for the French system, which is very difficult to approximate correctly. Everything else is within 1%, and typically below 0.5% as the system is growing. So we have near optimal solution. So what can we do now for actually having a real-time assessment platform? We take our optimization proxies, we replace every one of the optimization model, and now instead of taking 15 minutes, we take 5 seconds. It's a game changer for that industry. So, So you can see here essentially Gurobi on the left and the proxy on the right, and essentially you see no difference. They work exactly the same. They may be tiny, tiny difference, but essentially they work the same. This is a comparison of different methods. The method that I've shown, the proxy is on this side. You see that it's always satisfied, and you can see the optimality gap, which is in general 0. The other methods, you can see a lot of violations because they don't have this guarantee of having a feasible solution as we have. Now, what does it mean is that now you can do a real risk assessment on almost everything. What I'm showing you here is the financial risk. You see different methods. The method that you see Gurobi as well, if you would solve the optimization model. And then you can see that in general, what we do is we predict very well. We don't have false alarm, and we predict very well when there is a potential financial risk. And the only thing that is happening where we lose a little bit of precision because we are not optimal all the time is that you may overestimate that risk. But this is still a very good tool that you can actually use in practice. You couldn't use it before because it was too slow. So this slide is actually telling you the kind of speed up if you want to make sure that you are always within a tolerance for solving your optimization problem. And what you see there is that if you want to be within 1%, the speed up that you get by using primal dual solution, optimizing and minimizing the optimality gap, is that you have a factor of, you are speeding up the system by 3 orders of magnitude. So you are 1,000 times faster. So this is kind of remarkable, the fact that you can do this with these technologies. All right, so that was in power system. I'm going to show you another application where we don't train the proxy end-to-end, but we restore feasibility during inference. And so this is in the e-commerce industry. I'm going to show you, kind of results that were done with one of the largest package company in the world. They ship 10 million packages every day. So it's very, very large, and there is a lot of fluctuation in the shipping volume that they need to consider. So this is a paper with another set of students, not the same set of students that you have seen before. And so this is a way to think about it. So this is Atlanta. My students love to put Atlanta on the sea for some reason. But once you have these systems, Atlanta is actually not on the sea, right? So it's about, somewhere north there. So when you basically ship a package from Atlanta, let's say to Chicago, there is a primary road that the package typically that they like the package to follow. But if you don't do very good consolidation, you may use other routes as well. And so the rule of the game here is to consolidate the packages as best as you can so that you use the minimum number of trailers, trains, or planes. Okay? And so this is obviously you have to do that with millions of packages, but this is like a tiny example to show you this is where those packages have to go, and you compute the number of trailers that you have. But obviously you can choose where the packages are going. Okay, so this is the optimization problems. We won't go into the details of it, but roughly speaking, there are two important decisions that you make is, how many trailers you use on every one of these primary and alternate paths. And then the second thing that you want is to say, hey, where do the packet, which path are the packages going to? So the load here means, trailers. Flow decision here are the packages going there. Now, when you solve this optimization problem, it has very, very weak LP relaxation, which means that it's going to be very, very slow. And so the second thing that it has massive stability issue. So what you see on the x-axis is the load, which is increasing. The demand is increasing. And what you can see is that for and every one of these two pictures is giving you on a particular segment how many trailers are being used. For one particular of these, terminals. And so what you see here is that if you change a little bit, the demand, Gurobi is going to give you a completely different solution. So you see a planner looking at this, and then they see a solution, and 5 minutes later they see a solution which is completely different. You're going to make them, they're going to go crazy, right? So what do? We basically want to we typically have a plan at every point in time, and we want to stay as close as possible to the plan while still optimizing. And so we minimize the number of trailers that we are using, but we also break symmetries by trying to be as close as possible to the plan. And now suddenly, the trailers' decisions are much more stable with respect to variation in demand. And so learning this particular function that you see on the right is actually very, very easy, obviously. And so this is the first step. So we get a lot of historical instances for different parts of the year. We train a large machine learning model. This machine learning model is estimating the trailers, and then what we do afterwards during inference time is we solve, once these are fixed or expand it a little bit, we basically use a linear program for finding where the packages are, because the problem there is totally unimodular. And so we can actually solve that very, very fast. And so the difference in efficiency here is going to be, this is Gurobi taking about an hour and getting that quality of solution. This is the proxies, which gives the same quality of solution, but orders of magnitude faster. So we move to an hour to a couple of seconds, and therefore we can have planners in the loop. They can look at various scenarios. They can see what is happening. Okay, so again, this is a big game changer. If I show you the next slide, this is the business case. If you use optimization and the optimization proxies in real time, you may save between 10 and 15%. In logistics, this is massive compared to what they do in practice. All right, so this was the first part of the talk. This is optimization proxies. When you can get these optimization proxies, this is nice. When you can train them end-to-end, it's even better. What I'm going to show you now is learning to optimize, which is the second technique that we are going to talk about. And this is something that we use in large-scale supply chain problems. So what you see here is essentially the model that one of the largest supply chain software companies is using. This is based on the bill of material. You know which products you can build, which products you can build, how you can build them, and they have many ways to build them. Where do you source the products that you need for building them, and how you meet the customer demand. You have to do that for thousands of SKUs for a time horizon, which is about 3 years. So this is very difficult in practice. Again, this is like the optimization model. I'm not going to go into the details, but to give you a sense, what you have to decide is inventory, how you build the products, and also which suppliers you are using. So these problems have massive scale, a scale that I had never seen before. And they also have very, very large numbers. You are talking about big inventories of many, many different SKUs. And so this is one of the problems that you had. So this is in the pharmaceutical industry, 500,000 variables. And you see, optimality gap is within 1%, and we have an 86% reduction time. So basically, instead of 14 minutes, most of the time, you essentially have a few seconds for solving this. This is from the semiconductor industry, one of the largest suppliers of semiconductors. Again, you're going to see 0.3% of optimality, and that's the optimality with respect to the linear programming relaxation. And you see there a reduction of 61%. Typically, it takes a few minutes instead of taking an hour. So it's a game changer for the planners who are actually using this system. How do we do that? We do that in two ways. The first one is we do what is called predict, reduce, and optimize. We use a machine learning model for predicting what the decision should be. And we use that for actually decreasing the search space by an order of magnitude, or 2 orders of magnitude. So we predict some of the variable, not all, but that's what we do. And then you use this discrete solution space to find a feasible solution afterward, and you use optimization to do that. We still have an optimizer here, but what we do is we reduce the size of the optimization model by typically 2 orders of magnitude. So how do we do that? What do we predict for this very large? So what, if you have taken, mixed integer program, a course in MIP or LP, you know that many of the variables are 0, and that's what we are going to predict. We only predict if a variable is going to be set to 0 or not. Predicting the very large numbers is very difficult. So we predict them independently because there are so many that you can typically not predict them together. The machine learning model is too big. And so we use cross entropy to train the model. And one of the things that we do as well is that we penalize the large number. If a number is very large in the instance, we don't want to predict that it's 0. So we have a weighted scheme for doing that. And then, basically, once we have done that, we have a threshold by which we select the variables which have to be fixed to 0. And then we use a very, very clever idea. So what we do is that we are going to use some of the information which is inside the linear programming solver. We relax, the integer variable. We do the linear relaxation. And when you do the relaxation, you have this very beautiful concept of reduced cost. And when I teach linear programming, I tell people reduce, because most people have taken machine learning before. I tell them that reduced costs are a gradient. And if the gradient is very large, you want to actually predict that you don't want to make mistakes on those particular variables because they are unlikely to be 0. They are unlikely, the opposite, right? So if they're very large, they are likely to be 0. If they're very small, they are not likely. And you use that inside the threshold that you use for fixing the variable. So once again, this is interesting. You use machine learning, but you know what you're learning, and you exploit some of the information which is in the linear relaxation for deciding which variable should be predicted to 0 or not. So this is an example. This is like 2 million variables. Half of them are integer. This is the mean value of this variable, like hundreds of thousands. And so for most of the instances that we have, we can solve this problem within 1% of optimality, except for a couple of them. And so we were wondering, can we remove those? Because they are really annoying. And so, this is what we do. We enlarge the search space. You could actually use some of the things that Bistra and our group have done, which is like solving the problem using large neighborhood search to do that. But in this particular case, we do a little bit something a little bit different because we want to speed up, the runtime computations. And what we do is we basically look at variables which have similarities, like they are from the same time periods or they are from the same products line. And so we basically actually relax them, but during training, we have 2 phases. One is predicting which variables are going to be 0, and then we are going to predicting using deep reinforcement learning which variables have the potential, are potentially interesting to relax. And so we have essentially a learning model, a deep learning model. I'm going to show you some of the math there, which is essentially training which variable should be relaxed if we cannot find a solution of the right quality. And so this is very much like what AlphaGo is doing in a sense. So this is very similar things. We decide whether we reintroduce a set of variables or we exclude it. And the reward is the value of the objective of the optimization model for those. And essentially what you do is you're trying to learn the Q value, right? So and you predict it on the left, but you can also compute it indirectly using kind of the Markov decision the value function of the deep learning system. And these two quantities have to be equal. And so you learn it on the fly. You have different episodes that you run, and you want to actually make sure that these two so the fact that these two quantities have to be equal gives you the loss function that you need to minimize. So this is the loss function that you minimize, the difference between what you predict. 10 minutes. Wow. All right. So and then you get a magical result where essentially almost all the instances are solved. This is work that I wanted to show you this because this is work where Georgia Tech and USC, the Bistras group, are collaborating. This is results on a completely different problems, but again, you see massive improvement by predicting these variables. So, and also a massive, much better primal solution, much better dual solution. Let me talk in 5 minutes about this one. I want to show you something very unique. Can we solve sequential decision sequential decision-making problems using AI? And so this is like the state of the art for solving this problem is called stochastic dual dynamic programming. These are problems where you make a decision, you reveal uncertainty, another decision revealing uncertainty, and so on. And so I told you, state of the art is stochastic dual dynamic programming. Invented, kind of generalizing Bender's decomposition, one of my favorite techniques. The problem is that it's very, very, very time consuming. Jim Lutke and Merve Baudour had a really interesting idea by using linear decision rules. And we took this idea and pushed it further. And what I'm going to show you is that AI can transform a multi-stage problem into a deterministic problem. So this is my optimization problem. At every stage, you have some state, some decision variable. You have some action that you can take, and you have to satisfy the physical and constraint. This is how it looks like. This is like really annoying. You have this interleaving between mean and expectation, and you have these dependencies between the state variables, obviously. And so what are we going to do? We need a crystal ball again, and that crystal ball is going to predict, given the observation, what is the state in every one of this system. I want to remove the dependencies. If I can do that, these constraints are disappearing. When these constraints are disappearing, because I predict the state now, and the machine learning prediction doesn't depend on the previous states. So what is happening here is that you can see that every one of the subproblems are independent, right? So they are independent. So you can switch, you can permute expectations and min, and you get essentially a problem where you have the expectation on the right-hand side and then a deterministic optimization problem. Now, this is super cute. This is what I need to solve now. Okay, if I can guess, I can solve this. So what do? We predict. We have two phases. We predict the states, and then we solve optimization problem. Okay. Now, in practice, you have to pay attention to one thing. You are never exact in your prediction, so you have to relax a little bit the fact that you have to basically penalize the difference between what the action function would give you and the prediction. And when you do that, you can do self-supervised learning. So you do the forward pass the way I've told you. But the beautiful thing here is that the dual variables of this have only the variable that you predicted on the right-hand side. So you have a very nice way to differentiate, to actually backpropagate. And at inference time, the only thing that you do is predicting, and then you solve a deterministic optimization problem. So at inference time, you have transformed this very complex, multi-stage stochastic optimization problem into essentially a deterministic problem. I will go super quickly on the results, but the results are telling you that this is the state of the art. This is, the techniques that I'm showing you here. And the difference is like 3 orders of magnitude or 4 orders of magnitude in efficiency, and the training time is 60 minutes. This is for the Bolivian system, electricity and storage. How many minutes do I have? 5. Okay, rude. I want to talk about this one. Because this one is super cute. This is contextual stochastic optimization. So these are decisions where we have think about retail. A big retailer, you buy TVs or phones and so on, and they have to make a decision at every point in choosing the date at which they offer that to the customer. And once the customer accepts, they have to basically decide where they source it from, which DC, distribution center, or a store, and then they have to pick up the carriers that are going to do that. The key point is that you have to meet the deadline of the customer, so you lose these customers, and you have also to minimize your cost. This is something where you have about 70,000 orders every day. This is the platform that we have built. It runs in real time, and I'm going to show you a little bit the challenges super quickly, the challenges that you face. I'm going to skip this. I want to show you. So the problem that you solve is a stochastic a stochastic optimization problem that you see there. But the problem is that you don't have the distributions of the delays. You don't know in advance how delay a particular carrier is going to be. So you don't have the distribution. The distribution is not there. So you're going to use contextual information about the packages that you're ordering, about the DCs, about the shippers. So this is now your contextual stochastic fulfillment problem. The problem is that you don't have the contextual distribution either, but you can learn it. You can learn it and have a particular learning model to actually do that. But actually learning this is not easy because you have only observational data. And I'm going to tell you what this is. So when I make a decision to source from this DC and use this shipper, I don't see the other options. So I have no clue what they are. So it's much more complicated than most of the framework that have been used for contextual stochastic optimization because I only see part of the information. So what do? I learn a dedicated model for every one of the carriers. And then I get this beautiful framework. The problem is that the support is huge. And so what do? I sample the distribution. I use either the sample average methods, or I use a robust optimization with different types of budget. So what I want to show you is the kind of the impact that it has in practice. If you use the sample average, if you minimize expectation, essentially you get about 80% improvement. If you use robust optimization, you improve the worst case performance significantly. And then this robust optimization with a budget is really balancing these two worlds. You can solve most of this problem if you use robust optimization within 3 seconds, which is the time that you have, but not if you minimize expectation, if you minimize cost. But then what can you do? You can learn the optimization problem and use a proxy. And once you do that, this is closing the whole thing here, right? Once you have something like that, essentially you can solve the proxies in very, very little time, and you have essentially the same value, the same objective function as well. And so we put all these things together, and so you see contextual optimization and the proxy at the end of speeding that up. I'm going to skip this thing. This is beautiful, but too long. And so I'm going to conclude. And look at all the things that you're missing. But this is also super fast. And then essentially what I hoped that I gave you today is the feeling that if you combine optimization and machine learning and AI in general, you can do things that we couldn't do before. I showed you that we can do real-time platform, that we can do tactical planning for e-commerce platform, that you can do essentially retail in almost in the real time, almost optimal solution. And I also show you that you can actually do multi-stage stochastic optimization with orders of magnitude improvement. Now, this is the beginning of an area. I think there is a lot more to do, but there is indication that the combinations of these two technologies can really achieve things that we could not achieve otherwise. I hope I convinced you at least partly that this is an interesting area to work on. So thank you very much.
Thank you, Pascal. We have time for questions. You can use the mics on either side of the room.
It was super clear.
Okay, so there's 2 questions from the same person. The first one is there a public repository to access some of these tools? If not, are you planning to open source some of these tools?
Yeah, so there are 2 initiatives that we have. One is done by Bistra's group on distribution MIPLib, and we are trying to contribute as many problems as we can to that. This is a very nice resource. We have also something which is called PGLearn, which is also a repository of many other power system applications that you have seen, including the tools for solving them, and then the tools for evaluating new AI system, new machine learning. Yes, we are doing a lot of distributions of this of data, which is going to be public for some of the things that we have, and also some of the tools are available there as well.
Awesome. The next question is, how much is the offline training cost, both computational time and cost, for these ML models?
Yeah, so this is a good question. We don't need to have a massive data centers to do this. I show you that most of the time it takes less than an hour for training every one of these models. So they can be trained very efficiently. That's what I was telling you about, the power system application. You can almost train them during the day for the next couple of hours. So they have billions, they have billions of parameters, but they don't have, hundreds of millions of parameters. They are reasonable model compared to the large language models. So we can train them very fast. They're still big, right? So, and you have to be careful in how you model, how you architecture them, but they are reasonable in size compared to you don't need a data center. You need a really, really good machine from NVIDIA, for instance.
If there's no questions, I do have one.
Yeah.
Which is maybe because you went very fast towards the end.
Yeah.
So I'm a big fan of the decision rule approach to
Yeah.
sequential decision making, and I didn't quite understand though why we needed more than just doing the decision rules and then the classical
because what Murphy and Jim had done is actually putting decision rule inside the optimization model, but they were linear rules. And so if you try to put let's say a deep learning model in there, I think the problem becomes a very large, nonlinear, discrete, mixed integer problem, which is very difficult to solve. And so what we do is we disconnect the learning and the optimization. In a sense, you can think that's what we did, but we disconnect the prediction and then the solving. And so you predict the state, and then afterwards the solving is much easier because you essentially solve the deterministic version of. You have essentially revealed the uncertainty in one step. And so, the problem is really a deterministic problem there. There is the nonlinear aspect of the machine learning model are not there. They have been isolated. So we can do predict and then solve, which they didn't really do, right? So, and so I think this is like this disconnection is very nice. And then the fact that we can use a nonlinear model is also very nice. And also the nice thing here is that the way this is structured is that you can backpropagate to everything using only the dual variables of the optimization problem that you just solved. You see what I mean?
Then I have a follow-up question.
Phoebe, we can't hear you online. Is it on?
I'm on.
Here, let me give
I
you
can
this.
repeat the question if you want.
Oh, you can repeat
Yeah,
the
I
question.
can repeat the question so that I have time to think. So.
I do have a follow-up question. If you compared with nonlinear decision rules, so there, the literature on decision rules is very rich, right?
Yeah, yeah.
There's like polynomial decision rules, and in many applications, they've been shown, like in practice, by computing duality gaps, to be really, really good, meaning close to optimal. And so I'm wondering if you compare it to that, and there's really like a benefit in using these very deep models.
Yeah. So we did. I mean, I had to go very fast on that. So so I repeat the question. The question was, and still is, the question was, did you compare to nonlinear decision rules, because these nonlinear rules can be very, very accurate. And I think the answer is that we have a nonlinear rules, nonlinear decision rules, and it's very. As far as we don't know the optimal solution to this problem, right? So because it's a nonlinear, it would be like a stochastic dual dynamic programming model, which is where the subproblems are nonlinear, so you can't really do that. And so what we have, which is nice here, is the fact that we have nonlinear decision rules, but we can actually solve the problem extremely fast, right? So it's actually just solving an optimization problem in the end. And so I think that's the value, is that at the end, it's a decision rule in the sense that you are, so the decision here is that you predict and then you solve an optimization problem. It's not like the rule is not like the linear rule is not incorporated inside it has been removed in a sense. You see what I mean? It's not in the optimization problem. You see what I mean? And so that's the benefit here. And the reason we did that is to have speed, right? So the speed is what is important here. Yeah? And so on the application, I mean, I could go back to you and show you that at some point, but the key point is that we also compare of what if you had solved the problem not using, let's say the linear approximation of the power system, but the second order cone and so on, and still you get very significant benefit, both in quality and obviously in speed. Yeah, but it's a good. Any more questions?
No, I can shout very loud. Any more questions for our speaker? All right, thank you.
Okay, thank you.
Thanks, Pascal. Very nice talk.